Okay, first video we're going to talk about cardiology today. These are the things we're going to talk about. We're going to talk about the different kinds of cardiac cells, autorythmic versus non-autorythmic, or just your regular cardio muscle cells. We're going to talk about the kinds of channels that they have, how the action potentials work within the channels, how they depolarize, how it sends signals across the heart. We're going to talk about EKGs or ECGs, electrocardiograms. Talk about lead 2 because that's the one that's most common. We're going to talk about how those currents work and how it shows up on the EKG and what specific waves mean. And then if we get there, we'll talk about some pathological EKG stuff. So first we're going to start with, we're going to draw a lovely, lovely heart that is anatomically correct. Great. Okay. This is our septum. Okay, this is the left side of the heart. This is the right side of the heart. It's flipped for you, but if you're standing like this, left, left, right, right. Okay, I'm gonna get rid of those. We don't need those anymore. So here we've got left atria, right ventricle, left ventricle. This right here, we've got the bicuspid valve, we've got the tricuspid valve. Here we have the aorta. This is the aortic semilunar valve. Right here we've got the pulmonary trunk, goes behind, and then you've got your pulmonary arteries, and then you've got pulmonary veins coming in here. Here you've got the superior vena cava, inferior vena cava. Somewhere in there you've got coronary sinus. Whoop-de-doo. Okay. When we talk about autorythmic cells, there are 4 places in the heart where we find autorythmic cells. So around here, this is what's called the SA node, or sinus atrial node. Around here, so somewhere in here, if I remember correctly, it's right around here. That is your AV node, actually. If I remember correctly, it's like right here. Yeah. I will correct myself later in the description of said video where the AV node actually is. This is the AV node. Then there are parts here. Those are your bundle chain fibers or bundle fibers. Those are also autorythmic cells. And then you have little fibers here, here, and then it kind of just continues onward. Got those here. And those are called your Purkinje fibers. So these bundle fibers, and then these little things are Purkinje fibers. And so those 4 groups of cardiac cells, those are your autorythmic cells. And that's what we're going to go over first. If I were to draw just one of these, say I took one of these SA node cells and just blew it up really big. Okay, so these ones have several channels, and I'm going to draw what the action potential diagram would look like normally for these. This is threshold. Then I'm going to label this as 4, 0, and 3. Okay. Oh, you've got, dang it. Hang on. Okay, cool. Figured it out. There's just something I forgot. That stuff. Okay, so I'm going to draw in a couple channels here. label them. Great. And then in this one, yeah, got all the other fun stuff. Great. Okay. Cool. So I'm gonna grab this. And okay. So to explain really simply what is happening here. So within, oh, I need to draw that. Here's our SR. Here's our circuit pump. There's our ryanodine receptor channel. And then this is just a very, very crude drawing of a sarcomere. Okay, so stage 4, this is when it's just the funny channel. And this is action potential stuff. So we're measuring this in millivolts. So the reason this is called the funny channel, it also has the HCN channel. So H stands for hyperpolarized. So if the cell is below threshold or hyperpolarized, that means this channel is open. Or the CN stands for cyclic nucleotide. So if CAMP, I'll draw a little CAMP here. So if CAMP is bound to it, it's open, or if the cell is polarized, hyperpolarized. And so this is a cation channel. It allows sodium ions and calcium ions to come into the cell and to start depolarizing. When those come in and depolarize, this voltage-gated calcium channel will open and calcium will start to rush in. Calcium will rush in, you will have continued depolarization of this autorhythmic cell. And the reason it's autorhythmic is because of this funny channel. So here we've got the funny channel open, and that's bringing it slowly towards threshold. Once it hits threshold, this voltage-gated calcium channel opens. So we're going to write that right here. And then it's going to peak. And then once it hits this peak, that's when our voltage-gated potassium channels are going to open. So this is going to open, and then potassium is going to rush in to neutralize that electrical gradient. So it's going to repolarize the cell, and it's going to bring it back down to its resting. But the moment it passes threshold, that's when the funny channel opens again. Not Kirk, sorry. Funny channel opens again. And then it's going to start bringing it back towards threshold, and hence you can see how you have this constant beat. So for the SA node, this is around 60 beats per minute. So your SA node, AV node, bundle fibers, and Purkinje fibers, they all are like these kinds of cells. Your SA node is the most, most important, but not really. It's super important because it's what sets your pacemaker of the heart. It sets your heart rate without any kind of innervation from your brain or any kind of that stuff. It's around 60 beats per minute. If the SA node gets knocked out, the AV node will take over, and it's going to be a little slower. And then if the AV node is gone and the SA node is gone, bundle fibers will take over, and then eventually Purkinje fibers will take over. But as you kind of go down that cascade, your heart rate goes lower and lower. This GERK channel is important. So this is a G protein inward rectifying potassium channel, which is a really, really fun name for just some kind of potassium channel that will let potassium in or out, depending on the state of the cell. The GERK channel is largely used with parasympathetic innervation. So this is activated by, so you've got the M2 channel, and when you have acetylcholine bind to this, you have the beta gamma subunit, which will come over and bind to the GERK channel, and it will allow potassium to rush in. And that makes it so the cell is, no, just kidding. It will allow potassium to rush out So it'll hyperpolarize the cell, make threshold higher or resting membrane lower, and it's going to take longer for the funny channel to hit threshold, hence slower heart rate, which makes sense from the parasympathetic nervous system. Rest, digest, heart rate lower. That's what the GERK channel helps to do. Yeah, calcium will come in, it's going to interact with the ryanodine channel. Calcium is going to leave the sarcoplasm. We're going to cause this to contract. And then ions will send, like their sphere of influence will go through these. These are gap junctions. Your heart cells are connected. So we're going to draw heart cells. Just a very, very crude drawing. So they're connected by little gaps, gap junctions, which allow the influence of positive ions to pass through these spaces and to depolarizing following cells. So like this one slowly becomes depolarized. It's going to cause this one to become depolarized, this one to become depolarized, cause all the cells around it depolarized. And that's kind of how this signal travels from the SA node to the AV node, and then down these fibers, and then down these, and then to the rest of the cardiac cells. So that's our autorythmic cells. I'm now going to draw what your regular regular cardiac cells will look like outside of these autorythmic ones. We're going to use blue again, because I like blue, and blue is a good color. Okay, so we don't have funny channel, but we do have a fun channel that looks really familiar. This is our voltage-gated sodium channel, and then we also have voltage-gated calcium channels. Actually, I'm gonna write I. Here we have ITO, chlorine or potassium channels. I just stands for current, so it's something that happens when the membrane changes. Okay, so we've got IKUR, IKR, IKS, and then IKI. Okay, and then obviously we've got the SR, circa pump. Here's our ryanodine channel. I'll write circa here. We've got gap junctions, and then another thing. Wow, that was a fantastic drawing. Okay, the other one that we have. Oh, let me draw the sarcomere. Cool. There's my crude drawing of a sarcomere. Okay, and then the action potential, or like the electrical potential diagram, looks a little more like this. Goes up, hits, peaks, plateaus, and then drops, and then goes back here, and then does it again. Wasn't quite as good of a peak as I wanted. Peak and then drop down. We're gonna put threshold right around here. Okay. So this is, here's our plateau phase. I'm gonna draw which channels are open during this time. This is, I don't remember the numbers. I'll remember the numbers in a second. So this is our voltage gated sodium channels. Here we have our ITO potassium chloride channels. Here we have our I calcium channels, and then we have the IKUR, IKR, IKS, and then here we have our IKI. So all of the channels that are IK That just means it's some kind of potassium channel. So potassium is going to rush out, depolarize the cell. Okay, so what happens? You get some kind of stimulus from autorythmic cell. It comes in, it raises up, we hit threshold. Sodium channel opens. We have sodium rushes in, and it starts to depolarize the cell. Driving force for sodium is really high. Sodium rushes in, depolarizes, you peak here. When it peaks here, this channel, which I've represented as your ITO and your ITO chlorine and ITO potassium, those are really, really responsive channels to voltage changes. So when you peak up here, they open and they allow chlorine to rush into the cell, and they allow potassium to rush out of the cell following their gradients. And the goal is to hyperpolarize the cell, bring it back down to resting. At the same time, this calcium channel also opens. So I'm going to open this. So we have potassium rush out, and we have chlorine rush in. At the same time, we have this one which opens, which allows calcium to come in. And so this is why we hit this little plateau phase. So potassium is rushing out, chloride is coming in, we're starting to dip, and then the calcium channel opens, and so we start to plateau. And then during that time, we have these several channels open. So the IKUR, again, the I just stands for some kind of voltage or current, K stands for the potassium, the UR stands for ultra rapid. So it opens up super duper quick and then closes. So opens, and then the next one, the R stands for rapid, S stands for slow. So those open and continue to slow it down. And then here, this I don't remember exactly what the I is. I will get back to you on that one. This stays open, and this drops the cell back down to membrane. Another important thing to notice is, I'm going to draw this a little lower. So unlike skeletal muscle or smooth muscle, or in like neurons, the cardiac muscle doesn't drop below resting. And so the resting membrane potential for these is around, wow, that's not great handwriting, but negative 90 millivolts. So this is already super close to the Nernst potential for potassium. And so it doesn't hyperpolarize. So it basically just gets to resting and then is ready to go once it receives something else. So high increased calcium, it will cause the SR to release, interact with the hydrogen channel. SR releases calcium, sarcomere contracts, this contracts, gap junction sends it onward. And so these are your non-autorhythmic cells. And so really, really important thing is this plateau phase. Whether, depending on how long it is, tells you how quickly the cell is able to depolarize and when it's ready to contract and help the heart beat again. And we'll talk more about that. Cool. That's everything for cardiac cells. Okay. I'm going to erase some of this stuff. I'm actually just going to erase my whole heart, and then I'm just going to redraw it. Okay, now we're going to talk about EKGs. Yeah, that's a good heart. We're going to draw that. Here's our tricuspid. Here's our bicuspid or mitral valve. Here's our septum. Sorry, people are loud. Okay, atria. Here's our aorta. Great. Pulmonary, semilunar valve, aortic semilunar valve. Okay, and I'm going to draw in here's our SA node, here's our AV node, and then fibers. I'm not going to draw those in because they're not quite as important. And then I'm going to draw our leads. Imagine this is more tilted that way. Actually, I'm going to change that. I'm going to tilt it a little more. Yeah, so we got that. Wow, this is amazing. Great. Super thick. Yeah. Gosh. My heart just keeps getting better and better. It's okay. This is why I'm doing science and not like art or something. Because I'd probably suck at art. All right. Anyway, you can appreciate that this is a heart. Here's our right atria, left ventricle, right ventricle. You're a little A in there. So, to describe just really simply what happens when the heart depolarizes and how signals are sent. So the SA node sends signals all the way over the atria. And overall, that signal ends up going to the AV node. The AV node holds onto that signal for a little bit, sends it through all of the cells within that node, and then it sends it to the fibers and starts depolarizing the septum of the heart. And interestingly enough, the left side, because it's got so much more cells, it has to push blood through the aorta and then into the rest of the body. These cells will depolarize first, and then those will end up depolarizing the right side of the heart. And then we will get this overall general movement of the signal going down towards the apex of the heart, and then it's going to travel up to the superior sides of the ventricle. So then contracts, and then everything will depolarize, and it depolarizes from the epicardium to the endocardium, so out to in for the ventricle. Okay, now I'm going to draw a normal EKG for lead 2. And this is what lead 2 means. You've got the negative node up towards the high right side, so up here, and then left side down here, trying to follow the angle of the heart. So our first step, imagine the heart is not depolarized at all. Actually, I'm going to explain this first. So say I took some kind of cardiac cell, just so this makes a little more sense. Normally, when a heart cell is depolarized, you have a buildup of negative charges on the outside. Just kidding. Buildup of positive charges on the outside, negative charges on the inside. Okay. Right now, an EKG would be reading nothing. What the EKG does is it reads the kind of like the pole of the ions on the outside towards the electrodes. And because there's all the same charges on the outside, it doesn't feel any kind of pull. The moment that this starts to depolarize, so I've now got some kind of interaction between the positive and negative charges on the outside of the cell. The EKG is only reading on the outside of the cell, can't read inside the cell. So if we were to call this, say we've got some kind of negative interacting with the positives, and it's heading towards this positive. What this does to the EKG is it reads this as some kind of upward deflection. And so as it goes on, we peak, and then as the strength of that goes on, so the more negative charges you have, the less strong, and the more positive charges you have, the less strong the deflection. So you want a middle ground, and that's where your peak will be. So something like this, because you have 2 negatives, 2 positives, so you have 2 each to make some kind of deflection. Whereas if it's something like this, you only have 1 positive that can make an interaction with 1 negative, so you have a lower deflection. But because it's still heading this way, negatives towards the opposite electrode, we still have some kind of upward deflection. And then once it's all done, because there's no opposite charges on the outside of the cell, the EKG will read nothing, and it will again be flat. That makes sense? Great. I'm going to assume that's a yes. So what happens is if the cell then starts to depolarize, not depolarize, repolarize, We're going to get some kind of buildup up there. And now we're getting a positive heading this way. So it's a positive towards a positive electrode. What that causes is the EKG to start doing a downward deflection. So as we continue to repolarize the cell, over time it looks something like this. Yeah, great. So that's the basics of the EKG. Okay, so now we're going to talk about this and how that works. So I'm going to start using green arrows. So on the outside, we're starting to get, so over here, actually I'm going to use red because we can see the red super well. So all out here, we've got a bunch of positive charges outside each of these cells. And as the SI node sends its signal, it starts to depolarize everything over here. You start to get a buildup. I'm going to erase all of this green. Actually, I'm going to erase these greens. Okay, let's fix the heart, fix that. Great. Okay. Okay, so these arrows describe a negative tail towards something. So here we've got a bunch of negatives building up on the outside. We're just going to draw those in as negative charges. And those are having an interaction with all of the positive charges on the outside of all of the rest of the heart. So you would agree that we've got some kind of net movement this way, right? Yeah. So on our EKG, before, heart has nothing because there's no movement, and then we start getting this little depolarization, this negative interacting here. And then what happens, this depolarizes, well, this repolarizes, and the AV node holds it for a while, and it just kind of sits there. And so then we have this another flat line. Because average we've got here, let me draw a, go on, thank you. Just imagine I've got some kind of line between here and here, some kind of axis. Okay, so that happens, and then the AV node sends a signal through your bundle fibers. And if you remember, I talked about how the bundle fibers on the left side depolarize faster than the ones on the right because I've got more cells over here. And so they start to send signals this way. As we start removing the positives out here first. So we have negatives out here, and then we still have positives out here. So we're pushing that way, which interestingly enough, if we have, this is the angle of our axis for the electrodes, and we're pointing some this way, the angle towards the negative electrode is smaller than the angle towards the positive. So it's going to be some kind of negatives heading towards a negative electrode. So positive charges moving towards the same electrode, not positive. Charges moving towards the same charge electrode causes a downward deflection. And so in our EKG, we get some kind of little blip like this. And then what happens is the rest of the septum depolarizes. We're going to use green. I'm going to erase those, put a bunch of negatives. So this starts to depolarize. So our net direction of the depolarization is this way, which is very, very in line with the axis, and negative tail, positive electrode. So we're going to create a very, very large upward deflection. And then as this depolarizes, we still have upward deflection, but it ends up becoming less and less as more of the septum and the bottom of the ventricles depolarize. Okay, and then what happens is we now start getting the tail end of the ventricles, so the superior portions of the outside of the ventricle start to depolarize. And so that average vector is now more this way, which you can tell is pointing more towards the negative electrode than the positive. So we go a little bit lower. And then what happens? So eventually they reach all the way up. And so we're going to slowly get less depolarization, at which point the heart will be entirely depolarized. So you'll have negative charges all over the heart. And that's why we have this little space right here. And then what happens is the heart cells start to repolarize from outside in for the ventricle. So we have a buildup of negative charges all over the place, and then we start getting positive charges building up here. And so the vector for kind of like the charge pole ends up being this way. So here towards there, because we're building up positives repolarizing in this direction from outside to in. And so you can appreciate that these positives heading towards the negative electrode, they're moving towards charges outside, moving towards the opposite electrode will create an upward deflection. And so this is when we get something like this. And so each of these different waves has a name, and they're important to what's happening within the heart. This is called the P wave, and that happens when the SA node fires and the atria contract. Here, this is our PR segment. This is the time in which the AV node is kind of getting ready to send the signal off to the ventricles. Here, this is our Q wave. The Q wave is when the left side of the septum is depolarizing the right side of the septum. And then this is our R wave. R wave. We're going to write Q wave. So the R wave is when the majority of the septum and the ventricle is starting to depolarize. And then right here is the S wave. That is when the rest, so the superior portions of the ventricles are depolarizing. And then this is the T wave. And that is when the heart is starting to repolarize. So again, that buildup of positive charges on the outside, traveling up the heart. And that's EKGs. We have, when you've got the QRS, that's called the QRS complex. We have the TP interval, so the time in between when the T wave ends and the P wave starts, because this is a consistent thing, because this is caused from your autorhythmic cells. We have the PR segment, so how long it takes from the SA node to fire to cause the heart to wholly, completely contract. Then we've got the ST interval, kind of like how long it takes for the heart to repolarize. And that's EKG. And that's based off of lead 2, different kinds of waves, and how the current looks like within the heart measured from EKG electrodes on the outside of the body.